So today I'll be talking about planning agility. So the need for continuous planning, real-time planning, non-disruptive planning, and things like that, right? And a couple of other concepts around this. Now, we actually had two ways to intros, two quotes around this. So the first one is from Winston Churchill. So two proposals to prefix the title. And the first one was from Winston Churchill. And let me see if we can get rid of this. Okay, that's not really helping. Okay, it will have to stick there for today. Okay.
Do you want to try to remove it?
No, it's fine. Let's just keep it.
Okay.
So the first one is from Winston Churchill, and he said, "Plans are of little importance, but planning is essential." So what did he mean by that? Well, I think he meant by that is that if you have a plan, it's probably not going to go according to plan. There's always something that's going to change in the problem input and so forth before it actually goes into execution. But he said planning is very essential because, and that's very true, right? The worst thing you can do is have no plan. It's always better to have a plan that doesn't really go according to plan than not have anything at all. And we'll take a look what that means for our use cases and our business cases that we're working on, of course, right? Now, there is a famous boxer who said it in a very different way, but basically the same thing. And that's, of course, Mike Tyson, the heavyweight champion. What he said was when somebody asked him, so one of the reporters asked him, your opponent has this plan, is going to go do this, go left, go right, and so forth. And he just simply answered, like, everybody has a plan until they get punched in the mouth. And it sometimes does feel like that. If you have a plan and once it goes into execution, just before something happens and the plan is very much disrupted by that. So let's take a look at what kind of planning disruptions we might see. Well, I would argue there's two types: a local disruption and a global disruption, or at least a disruption more across the board of your company. Even if you have a company that's, let's say, only active in France, you might see a disruption that actually affects all of your stores or all of your locations and so forth, right? So, and let's take a look at some examples of both of these. So the local disruption one is quite simple. You have a plan. You're going to take a certain employee will be covering a certain shift or a certain task, or a certain technician will be driving a particular vehicle, and that person is sick today. He sends that in maybe the day before, maybe an hour before, maybe just at the moment that the shift actually is supposed to start. So that's a very disruption because you were presuming that person would do that job. It's actually an additional problem if that is a person with a rare skill, and you might not have a backup for that and so forth. So that becomes interesting, right? There's also global disruptions. And so one particular global disruption was the September 11 attacks in 2001. These particular ones affected especially the airlines, because the airlines traffic was shut down in North America for 2 days. What's interesting about this story is that many airlines at the time did not have any form of automated planning. And it took them up to 5 days to actually get their airplanes in the air again. So in 3 extra days they lost, not because they couldn't fly, simply because they couldn't get their plans together to actually fly those planes. And you might wonder, why is that? Well, it's quite simple. When you send a plane, let's say from Paris to Washington, and that flight gets canceled, well, that physical airplane is not in Washington where it's supposed to be to go to pick up, to do the next flights leaving from Washington, right? And the air crew which is supposed to be in that airplane isn't there either, right? And the airplane you're going to use immediately afterwards, but the air crew will have to sleep, and so that's going to be in another flight, and then they're going to fly somewhere else, right? So the moment that you basically, say, we pause the whole schedule for 2 days, then, and let's say it happens on a Monday, by the time it's Wednesday, everybody's supposed to be somewhere else than they're supposed to be. And you have a global disruption across the whole thing. And so the airlines that actually had at least some form of automated planning, even if it wasn't a very good one, they could actually get their planes in the air much faster. They did it actually after they'd only had a 2 or 3 day delay, unlike the 5 day, which most ones had. Now, a little bit later, a few years later, there was another one global disruption, and again it hit the airlines. This was the volcano eruption in Iceland. I'm not going to pronounce the name, Duncan, of that airplane before you ask, but it shut down the air traffic in Europe for 8 days. So 8 days they couldn't fly, and afterwards again they were in the same problem, right? And of course, we all know that afterwards everything has been brilliant in the airline industry. I mean, no clouds on the sky, of course, except of course for this year. Again, they got hit quite badly, and due to many flight cancellations, it really affected all of their planning. And again, automated planning is a good way to deal with planning disruption, right? So there's this paradox that I often see. I sometimes see that, okay, we cannot automate this kind of planning because the plans will change. And so we need the humans will need to change the plans anyway. So it's better just to let them do the plans. That works as long as the plans are very isolated and as you don't really care about optimizing those plans and so forth, right? But when you want to optimize those plans, well, and when you have global disruptions and so forth, you really need to think about to automate your replanning, to just be able to deal quicker with disruptions, even if they're local or global, doesn't really matter, right? But of course, this has an effect. You need to make sure that the code we write, the OptaPlanner implementation we do about this, or with any other constraint solver, that it actually is able to handle planning changes, right? So what are the techniques here? So the question is how? How do we deal with planning agility? And I would wish there was a single answer, like this is the answer. Now we do have the answers, it depends what you want to use, and sometimes you want to use combinations even. Now, before I go into what exactly you want to use, I need to ask you a couple of questions. So what is your publication deadline? Think about that for a minute. Think about your planning problem, your scheduling problem, and ask yourself, what is the publication deadline? So what is a publication? Is the moment when whoever's doing the planning, the human planner, the machine, the manager who's sitting behind the machine with OptaPlanner solving it, actually says, okay, it's ready. I'm going to give it to the employees, right? So I'm going to tell the employees when or how or where to work, or any combination of that, or the machines if no employees are involved whatsoever, right? But I'm basically going to publish the plan. And so what I notice is that every use case has a publication deadline, right? And it's a good question to ask when you come into a new case. So what is your publication deadline? How much time in advance do you need to share your plan with everybody who's involved in that plan, or at least the majority of the people who's involved in that plan? And so what happens is in technician routing, for example, like the vehicle routing case that Satish showed earlier, it could be up to just 1 hour before the department. The technicians know that they need to show up at the depot, and they know they'll be going home in the evening. And in between, they don't really care where they have to drive to in advance. They just figure it out. They will arrive, and they will look at their route. They will put the right stuff into their vans, and they will leave. And as long as the hard constraints of the routes are met, that's all fine. For school timetabling, for example, you can't do that. You cannot say to the teachers and to the students an hour before the new school year starts, look, here's your school timetable, like the case that Radovan showed. You need to do that. You need to actually stop quite a while before that. I would argue a week, but I've seen schools actually do it just a day before, because school timetabling is a very hard problem, especially if you do it manually. As Radovan also showed, just making sure that the hard constraints are met is already extremely difficult, let alone soft constraints, right? So again, you want to do this way before the end of the vacation, or maybe even a week before the school starts, or maybe a month before the school starts. I mean, you are affecting the lives of the teachers. You will be affecting when they will be home during the week and when they will have to work at school. Guards and nurses, the same thing. You are affecting people's lives, and much more randomly even. So every time you release a new week for the guards, or a new nurse for the nurses, you will be deciding if that nurse can go to that party. Well, nowadays she won't be, of course, but if she can at least be home with her family, take care of the kids, or he can take care of the kids, and so forth, right? So you want to do that sometime before. And what I've noticed is it kind of depends on the sector and also the company and so forth. But with nurses, it tends to be more in advance. But their schedule seem to be far more erratic than guards. So guards typically have like 4 days in a row off, 4 days for late shifts and so forth, right? And any sort of combination. And the last one is the facility location problem, which I haven't talked much about it, but this is where we have a quick start for this now, a Quarkus quick start for this now that we're building. Jira did a really nice one about that. And what we're doing in there is we're assigning but we were deciding which locations we will open a new store or a new warehouse or something like that, a new facility. And we're going to try to do that as optimally as possible. There's a variation on this with 5G masts and so forth. But the thing is that this happens way before we actually do it, right? We actually execute the plan. This actually happens like 6 months before it, right? So what we see is, if you just visualize this for a minute, whatever kind of planning we have, there is this publication deadline, as you see here, and there's this execution start, right? So when the publication deadline, we need to deliver, we need to send out a plan before the publication deadline hits, right? And this is the moment of publication, of course. Usually they coincide. People usually wait till the last moment to actually release the plan, right? And this could be hours, like in this case. So the execution of the plan is on 28th of February at 8 o'clock, and it could be like for vehicle routing case, we actually deliver it at 4 o'clock. But it could also be that it's weeks in advance, like for nurse rostering or guard scheduling, right, where we deliver it weeks in advance. Even though nurse rostering and guard scheduling would be called operational planning still, it's far more out, right? It's far more advanced, far sooner. And then there could be, and there's cases of strategic planning, like hiring new nurses or hiring new guards or deciding where to build a warehouse and so forth. And you'll be actually figuring out your plans months in ahead, right? That's really on a strategic level. And what's interesting about these things is how they affect each other. You could have strategic planning cases that affect your tactical planning cases, which can affect your operational planning cases, right? So let me just give you some examples of that, of these. What's it? Just have a feeling what kind of planning problems you have there. So for strategic, could be for nurse rostering, could be, do we want to expand the maternity wards, right? Do we want to allow more women to give birth in our hospital because there's a need for that, for example, or another hospital is closing? And when we do that, of course, that will have an impact on our nurse scheduling because we will need more nurses and so forth, right? And more doctors and so forth. Technical. Do we want to hire a respiratory specialist? Do we want to hire a maternity nurse? Because a normal nurse cannot just work in a maternity. A normal nurse is not a respiratory specialist. For example, around COVID, respiratory specialists were the nurses you want to hire because they have that rare skill that you will just have a high need around, right? And then operational, of course, we need to assign, do we want to assign Monday shift to Anne? So if we hired extra respiratory specialists, if we built that maternity ward, that will actually influence in the options and the freedom we have to assign Monday shift to Anne. It will actually depend on it. So these planning problems depend on each other. Each planning stage feeds into the next. So just to give you another case where it's really where it's even more tightly ingrained, especially for trains and airplanes. This is sometimes a bit mind-boggling. But strategic-wise, do we want to stop in Philadelphia? So when we have a train going from let's say Washington to New York, do we want to add a stop in Philadelphia? It means that the train ride is longer, but we could carry more people, sell more tickets, right? Technical, do we depart at 7 a.m.? This is influenced by the whether or not we stop in Philadelphia. If you have to be in 12 o'clock in New York because that's our time slots to actually arrive there and the train track is available, then we need to leave earlier in Washington if you're going to stop in Philadelphia, right? Operational, which locomotive and wagon will we use? Will we use the fast locomotive, which can actually get those top speeds or not? How many wagons are we going to add behind this? And again, this matters whether or not you stop in Philadelphia, because the more people you carry, the more wagons you need. It could also be affected by if you leave at 7 a.m. or not, because that wagons might still be in use on another train. Those locomotives might still be in use on another train. Right? It all depends, right? So especially in those cases, those things really depend on each other. But here's the big problem, right? If you look at these cases at their publication dates, they are separated by time, right? And while you can solve, when two people are separated by location, you can solve that by coming together. If you are separated by time, unfortunately, as far as I know in this universe, you cannot. So, which basically means that this is the same for publication dates of planning problems. Planning problems that have a different publication date cannot be using the same solver instance in OptaPlanner. Right? So if you have something that have different publication dates, don't use the same solver instance. Don't start adding multiple planning entity classes. Don't start adding multiple planning variables. It's not going to work. You need to have one solver that comes up with a solution that gets published, and then sometime later, the next solver will get that as get the decisions that are made in the first solver, in the strategic solver, as basically hard constraints in this solver. And of course, you can do some feedback mechanisms like Banner's decomposition and so forth. But big point is that basically this one comes first and sets the terms there, right? And if this solver doesn't do a good job, or if it's too tight, if you try to save too much money on this level, turns out there's too few employees actually get all the solving done, then you have a problem here. And of course, there are solutions there. We call this over-constrained planning. In that case, you start hiring intern nurses or something like that, and that becomes quite expensive. So there goes your money. Gain becomes a money deficit, of course, right? But you can get that feedback back to this department. Another interesting thing about these is that when you look at this, Conway's law applies. So what's Conway's law? Let me read it out for you. Any organization that designs a software system, he just said a system, but it's a software system, will produce a design whose structure is a copy of the organization's communications structure. So let me try to turn that around just to make it a little more understandable. The planning problems solved by different groups should use different solver instances, because if two groups are, so if it's not one, if two groups are today solving a planning problem, and you're going to try to replace that by a single solver that solves the whole problem for all groups, you're going to run into a problem that you're not just trying to solve a software problem or software architecture, you're going to try to solve an organizational problem. And so you better study some parts about human resources and so forth, right? Change management, basically, in an organization, it's a very, very different challenge, a very, very big challenge. I'm not saying it's not possible, but the advice I always give is during the first year in production, make sure you do it the exact same way as it's being solved right now by either humans or existing software. And the next year, second year, think about throwing some of these, if there are multiple partitions or regions, think about throwing these together so you can have additional scale benefits. And the third year, it's time to let's take a look at the once you have both solvers running of both the operational level and the tactical level, or the technical level and operational level, then of course, now they're on a different stages, right? But if they have the same publication deadline, this third year, then you can actually start trying to merge those two groups, but then you have a change management problem. So it's the software part is actually the easy part of the challenge there, right? So what does this mean in practice? So here's a case. We have a train wagon to decide which train wagon we will assign for a train ride, for example, for the train ride today leaving at 9 o'clock. And we will also have to decide where this train at which platform it will stop in New York. So if you remember in any train railway station, you'll see there's multiple platforms. So it has to decide which one will stop. And some of these platforms are longer. They can accommodate for longer trains. Some of these aren't shorter, right? So the deciding on how many wagons and which wagons you put on there could actually be an influence to which platform you could use. And you could probably say you should solve that as one single planning problem, because you both decides the wagons and the platforms at the same time. And that's probably in theory, in utopia, the best way to solve it. However, if today your train wagon group and your train wagon department is a separate group from your train platform department or platform decider group, don't do it like that. Don't start out like that, because it's just you're trying to walk up a wall. Take the stairs. Start with first implementing this, get this in production, and then start unifying them, right? So here we can see the wagon solver being called, and at a later time we do the platform solver. So, second question: do you assign to time? So what does that mean? So sometimes you don't assign to time. So here's an example where we don't assign to time. We're assigning the cloud balancing problem processes to computers. You don't see any notion of time there. Yeah, it's just, this is the state we want to get to, right? If you make any changes, we'll just reassign the processes to get to that new state. There's no notion of time in this domain, right? So you can basically see this, because if you actually looked at the domain model and so forth, there is no notion of no java.time import. And I'll explain later why this is important, but this actually influenced some of our choices later down the line about replanning. So the other option is, yes, my domain has time, but the planning does not assign time. So what do I mean by that? So here's an example of the hospital bed planning problem, where we're assigning patients with a certain name, with a certain arrival date and a certain departure date to a bed. So we're deciding which bed, in which room, in which ward this patient will be. And now the interesting thing about this is that we don't get to choose the arrival date or the departure date of the patients. That's already decided together with the doctor earlier. That might be a tactical planning problem, and this is an operational planning problem. So that was a different solver maybe, or maybe it was handled just by picking up the phone and saying, oh, look, there's a gap in the surgeon's agenda. Let's do it then. Doesn't really matter. What we need to do is we need to figure out what's the best bet given a number of preferences. Like, for example, this person wants a single room, and of course, if we put people in a double room, the gender should match. So don't put a male and a female in the same room in the same night, right? The hospital bed does not change the patient's arrival or departure date. So this is the planning variable does not affect these things. So that's an interesting thing. So that's another case. But then of course we have the third case. But before we jump into the third case, where OptaPlanner actually does change the assignment to time, let me talk a little bit about Java time and so forth. You can see I'm here importing a local date time. Oh, that's a mistake. But I'm importing a local date. But by the way, don't use java.util.Date for time manipulation. Let me just rant for you about that for a second, because asking java.util.Date for a calculation around time, it's asking like your bartender how to treat cancer. Yes, you'll get an answer. Yes, it will sound good. It's not going to be accurate, right? Java.util.Date has problems and issues all around it. Daylight saving time is just the tip of the iceberg. Now, some people say, okay, in the old days, it then said use Java.util calendar. Don't use that either. That's even worse. That's at last asking your dog how to treat cancer. It will just bark at you. At least that's my experience. It is an horrible API. Luckily, they realized that the Java founders and so forth. So what they did is, thanks to Stephen Colborn's work, by the way, they added a java.time package. And since then, we have brilliant support in Java for any time manipulation. So the big two to know there is local date and local date time, right? So local date if you just have a date, and local date time if you have a timestamp. If you are a company that's all across the world in different time zones, you might want to change this into zoned date and zone date time and so forth. But of course, that depends on your use case. I would recommend, if you do not have that use case, please stick with the local date, right? Default to local date until proven otherwise, right? Or local date time, right? Or local time, depending on the case. So here's a case where, let's say we're in the case where, yes, our domain has time and those planning assigns to time. So then we need to pick a good model, right? So let's take a look at a couple of the options you have. Assigning time to planning entities, because it does affect our planning agility problems, right? So the first option you have is I'm going to use the time slot pattern. This is one of our design patterns, which is explained in our manual. But basically what you're saying is, and we use this for the school timetabling problem, for example. We have a lesson like math theory or chemistry or math exercises. We're going to assign it to one time slot, right? And also in this case to one room. The point about this is that the time slots, as you can see, this one goes from 8 to 9, this one from 9 to 10, but here's a recess break, starts at 10:15. Point about this is that we cannot assign math theory to 8:15. No, we can only start it to the time slot that starts at 8, right? All the time slots are equal in length. Do they have to be? In fact, actually for this pattern, they don't have to be. For the conference scheduling example, we have conference talks that are different in length. So like here, lessons are different in length. But of course, the long lessons will only go into the long time slots and the short lessons will only go into short time slots. You can't mix, and so that's one of the limitations of this pattern. Now, so yes, here we have the same duration for all planning entities. You can extend it a little bit as long as we cannot say we're going to take 2 short lessons, put them in a long time slot. So that's once you have that, the time slot pattern is no longer your friend, is no longer what you're looking for. Another option we have. So let me just show you what's the code behind it. So we have a lesson here. This is the school timetabling problem. Well, actually, Radovan just showed it, but just to take you to it again, the lesson has a subject, a couple of other properties, and it has this time slot variable, and of course that's importing some Java load time here. Notice here that in this particular slot, and this is something to think about, we're not assigning a lesson to a date. We're assigning to a day of week, like Monday. Monday is not a date, right? It's not, the 1st of February might be a Monday, but the Monday is not the 1st of February. It could be the 8th of February, and we are assigning it to a start and end time. So that's quite interesting. So why is that? It's because we schedule 1 week for school timetabling, but we repeat that every week until the end of the semester, right? So it's really, we're just scheduling 1 week, and then we just copy paste that forward. So that's why it doesn't even have a date, because it's not, it's not just the first week we schedule it. We will copy it to the other weeks. Besides the time slot pattern, we also have the time grain pattern. So the time grain pattern is actually a more flexible version of the time slot pattern, I would argue, where you're saying instead of assigning these lessons, or in this case meetings, to a full time slot, we're assigning it to a time grain, which is basically the start of a time slot, right? So these time grains are, you can see that as starts of time slots. But so what we do is we fill up the time, the planning window with time grains of a certain granularity. In this case, it's 15 minutes. I wouldn't recommend going to 5 minutes. I've seen cases where 30 minutes and hours or a day fits, then use those. I've seen very few use cases where 5 minutes actually makes sense. If you tell people to be on time on 5 minutes, they could do it, but it's unlikely that you want to schedule things on a 5 minute granularity. Going below that, saying to somebody, your talk starts at 8 o'clock, 0 minutes and 5 seconds. That's saying it, that's useless. Just say it starts at 8 o'clock, right? So that's why. So when you do time grain pattern, think about your time granularity. And the reason I want to keep it big, like 15 minutes, that's actually already very small, is because it affects the search space and also the efficiency of the solver. In fact, time grain pattern isn't that an efficient way to solve. We'll look at the chain pattern in a minute, and that's usually far more efficient. What is the advantage of this? Is that it can pick the gaps. So it can decide, look, I'm going to keep a gap in this meeting room, in room B, during time grain 7, which is apparently from 9:45 till 10 o'clock. We'll keep a gap here. And you could make that, 2 time grains or 3 time grains if you just take this brown event and just move it down a little bit to the right. What is a requirement here is that all of your meetings are rounded to a number of time grains. So like the green one is 4 time grains, the yellow one is 6 time grains, the purple one is 1 time grain. So you need to actually specify in a multiplicand of 15 minutes in this case. If you look at the change through time pattern, which is of course the pattern we always use for vehicle routing, task assignment, project job scheduling, and so forth and so forth. This is a very common used one. Is that we basically don't assign these planning entities to directly to a time. We just assign them an order. We say Anne first does the French taxes, which is task to calculate the taxes, and then does the Spanish taxes, right? And Bad does first the Dutch taxes, then the Belgian ones, and then the German ones. And the interesting ththing about this, these calculations can now be any amount of time. They don't have to be divisible by 15 minutes. So this one is 52 minutes, this one is 47 minutes. So basically, the next task, the next entity in the list starts when the previous one ends. So there's no gaps to decide. And that doesn't mean there's no gaps. It just means there are no gaps to decide. Because here, OptaPlanner can decide in a time grain pattern, I'm going to leave 15 minutes or I'm going to leave 30 minutes, which is a feature you might want. But in many cases, what we see is that we can actually use a chain pattern, which is, again, far more efficient usually, and still have gaps. So how would that look like? Let me show you. Here's again the chain through time pattern, but this time there's gaps in there. So how do the gaps work? Well, this is a vehicle routing problem. Anne is going to drive to the WTC building. Then she's going to drive to Wall Street. And then the next day she'll drive to 44th Street and then 49th Street. Now, the interesting thing is when she does a Wall Street, drives over there, it actually crosses her lunch break. So the moment it crosses her lunch break, we actually pad this task or this delivery or this drive with an hour. Because we know somewhere in this time, she will actually, stop for an hour with working and get some food, right? Get some lunch. Then what we see is we get the same thing here. So then there's a sleep thing. So and then we notice, well, we could, after we go to Wall Street, we could still drive to 44th Street, but we're never going to get there before 5 o'clock. So our variable listener, our shadow variable listener, what it actually will do is it will actually push this forward and start the arrival, the arrival time at 9 o'clock instead of trying to append it here. So we have some minutes forwarded. But again, it's also the shadow variable that's going to pad in this lunch. This is all done by custom shadow variable. You can see that we do the same with vacations and sleep and so forth. We just pad in the time, the gaps, to make sure that we fulfill our requirements, such as making sure that every employee has a lunch break, or gets to go home at 5 o'clock, right, and so forth and so forth. So that is how we can actually enrich chain patterns with gaps. There's a fourth pattern called the time bucket pattern, which we use, for example, for elevator maintenance, scheduling, and so forth. What you basically do is you take a time bucket of, let's say, 1 day or 1 week or something like that, and you add in a number of tasks, a number of jobs that need to be done. And then what happens is you make sure you have a certain capacity on how many, how big those jobs can be. For example, here you can do 3 yellow jobs of sewer inspections, and together, as long as they don't take longer than 8 hours, we can throw them into one bucket for that. This has some downsides if you compare this to vehicle routing, because we don't decide the order in how we will go from A to B and C, but it has a big upside, and that's because there's far less micromanagement here. While if you use the change through time pattern, you're telling to people in which order they will do their tasks, right? In a time bucket pattern, you're just telling them, here's your tasks, how you do them, and you figure out which order you want to do them. You can still optimize on a whole bunch of things, like if these tasks are in different locations, try to get them at the locations that are near each other. But you're not going to get the vehicle routing efficiency of actually getting the shortest route. So it's a trade-off, right? But in many cases, it can actually, it's a good idea to do this. Depends on the use case. Not for vehicle routing though. So now that we learned that planning variables, planning entities can be dealing with time, and can actually assigning them in time can be a planning variable or not, and still time could be in there. let's talk about some of these ways to actually solve these replanning cases, right? So do you replan every week or every day or every hour? And if the answer there is yes, then continuous planning is probably your thing. So what is continuous planning? So if you remember from employee rostering, we're assigning employees, as you see here on the side, with different skills to shifts. So there's a morning shift, afternoon shift, or a night shift. You can see some of these shifts have skill requirements, and sometimes they're free, right? So what happens in continuous planning is, well, we make a planning, right? This is the publish notice, and before the publish notice happens, this is the plan we make. We're telling basically that these 3 nurses, that this first nurse, this first is a designer actually, will do 3 morning shifts and then a late shift, and the last nurse here, for example, will do 4 night shifts and so forth, right? And then the middle one has a couple of days off. What we actually do is in continuous planning, we change it a little bit. Instead of planning 1 period, typically 1 week, what we do is we do that 2 or 3 times in length. So we actually plan 3 weeks. The first part we call the final draft, and the rest we call the draft. And after that we call unplanned. So why do we have a period that's unplanned? It's because we cannot say let's plan until the end of time, right? Until the heat death of the universe or something like that, right? No. What we need to do is we need to limit that. Just memory restrictions on CPU and so forth, of a machine and so forth. So and it's also not interesting to look forward than maybe twice or 3 times the draft period. So but we don't want to just do the last draft, because that would paint us in a corner. I'll get back to that in a minute to explain it better. So what happens a week later? Well, a week later we plan it again, but this time this part, the final draft, was published already, right? And so we're now Tuesday or Wednesday or Thursday. So this part was published. We can't change it anymore. We're planning a new part, so the next few days. And of course, we've extended the planning. The planning window is again the same length. So we've actually extended we added an extra week at the end, right? So, and when we kept doing it like this, again, a few days go by, and then again, we need to deliver a plan. What we actually get is, this is called continuous planning. We get a planning window that moves from, of course, through time, where we always have the same amount of time that the same planning window that we're solving. It's always the first part of that, usually the first week. That is the final draft, and that's the part that we're delivering. That's the part that we're publishing, right? The other parts, as you can see here, they just go in there next week, they get replanned, and they might have changes. Like, for example, here we had a night shift. Well, here that turned into a day shift, right? So why? Because new information came in the back, or maybe some of the requirements here changed. Maybe somebody asked for a free day before this was published, and we couldn't do the original drafts anymore. So this is continuous planning. So when you do continuous planning, you need to make sure that anything that's in the history, all right, that doesn't change, especially if it's already happened, right? So what you do is, here we have a shift where we have the start and end date, and we need to assign this to an employee. Notice that we don't assign the shifts in time. We actually assign the employees in time, if you look at the other way around, because when we assign a shift to an employee, the employee gets assigned to 1 or more shifts, right? But anyway, we have a Boolean history here, historic or something like this here. And we put a planning pin on that, which basically means that if this Boolean is true, then this shift will not change its employee, and the employee will not be changed by OptaPlanner, by the solver. And so that's a good way to make sure that, look, OptaPlanner, you can change everything in the draft piece, but you can't change anything in the historic piece or in the published piece. So if you want to do it on the published piece, this is the exact same approach, of course, but now this is called a Boolean published. And of course, anything that's historic is also published. So the historic ones won't change either. So if this one is true, then we won't change it anymore. But let me think about that for a second. The shift hasn't happened yet, but it is published. So we have not the intention to change it anymore, the assignment. Doesn't mean it won't change. Well, probably. Let's think about that let me come back to that in a few slides. So continuous planning with the rotation. So how does it work? so here's a more elaborate example. We have a number of shifts, so morning, afternoon, and night shift on every day. So every column here is one day, like the 1st of February, 2nd of February, 3rd of February, and so forth. And right now we are about, I guess, the 4th of February or something like that. We have a published deadline to figure out what we're going to do 3 weeks from now, by the 8th of February, right? So we need to decide what is the plan for the 1st of March. So let me just show you. This is the plan that we need to make. This is what our solver is solving, the draft part. These parts, the published part has been published earlier, but we have a contract that says to our nurses or security guards or whatever the case may be, that 3 weeks in advance, we're going to tell you when you will be off in the week of 1st of March, right? So when you can meet up with your friends because you don't have to work. Now, as this now line gets closer to the publish line deadline, before that happens, we need to deliver this part. So when that do, you decide, okay, this is the final draft. That's that week that we're going to publish. So the publish length here is just 1 week, and actually in almost all cases I've seen is 1 week, if at least it's a week granularity. We have cases with hour granularity too, of course, but that's not what I'm explaining here. What basically happens is this final draft becomes published, written in stone, or at least wood, I would say. I wouldn't call it stone. And the rest stays draft, and we add, of course, another, just like I've shown earlier, another number of shifts to the end of the the planning window, which will need to be assigned during the draft, right? This is basically what happens after we publish that 1 week. So what do we have here? We have a publishing deadline, we have a publish notice, we have a publish length, and we have a draft length and a final draft. So a lot of terms here. Things to know is that the publish notice is how much time in advance the people need to know their schedule. The draft length is how big is your planning window that you're solving with a normal planner run. So when we're changing the normal things, because we will also maybe we'll need to change the published part, and I'll get back to that later. But here we're just running the solver through the draft part, right? So don't paint yourself in a corner. How do you paint yourself in a corner? Well, for example, you assign all of your respiratory specialists, which you have, which is a rare skill, to the last shift of your planning window. So if we look at this and we go back a second, we assign all of our respiratory specialists to all kinds of shifts here at the end, including normal shifts that a normal nurse can do, but we just, they can do those shifts too, so we assign them to it. The problem is not here. This will be a perfect schedule with a very good score, but when you then try to solve this problem the week after it, all of your respiratory nurses are unable to work that first day, or at least that first shift on that first day, because they just did a night shift the day before. So you painted yourself in a corner. So don't do that. And how do you do that? Well, what I've done here in this example, you just have a draft length, right? You have a draft length which is longer than your published length, and then the amount of the week that you're publishing. Instead of solving for 1 week, you solve for 2 weeks or for 3 weeks, right? So your draft length must be at least your published length. That's a good advice there. Okay, so you can see how that affects that. So okay, so the publish notice can range from long to short, weeks or seconds, right? So in weeks we do employee rostering or pharmacy on duty scheduling, and seconds can also happen. Runway scheduling in an airport, or gate scheduling in an airport, platform scheduling for trains. And in these cases there might not be humans involved, but you're still doing continuous planning. There's time involved, and as time goes by, you need to schedule things. Often you will combine continuous planning with real-time planning, which I'll get to in a second. So what we notice here is the domain must contain dates or timestamps. So you probably see a Java time in there in your domain. And the planning windows must overlap. If they don't overlap, you're actually in the case of school timetabling, right? Where you just say, okay, I have one planning window that I'm solving, and I publish that, I might actually copy that, but the next one, there's no overlap, right? So you need that window overlap before your continuous planning, before you need to use like the planning pin trick and so forth to make sure that you replan every week, right? Otherwise, it's just two separate planning problems who don't have anything to do with each other. So in school timetabling, planning the first semester or the second semester, they are completely, they are independent, right? You might some decisions you've made in the first semester might affect the second semester, but there is no continuous planning there. So the next question is, will the published plans change? Right? I've alluded to that. It's called, and if they change, we want non-disruptive replanning. So how does that work? So remember our multi-stage planning here, right? So we had strategic planning decided months in advance, tactical planning weeks in advance, operational planning hours in advance. And so at that point in time, we figure out that's the plan, that's how it's going to be, and then things like this happen, right? In a strategic plan where you decide to hire new people, maybe somebody resigns and you would have to hire more people, but it actually takes sometimes, in some organizations, it could take quite a long while to get the budget around to actually hire somebody. In technical planning, you decided that nurse is going to do that shift, and then all of a sudden it turns out that particular nurse needs surgery and will be, and she tells like a week in advance of the plan execution that they won't be available for that plan. You will need to figure out somebody else who does that job, right? But meanwhile, your plan is published, right? And you're likely going to have to change the published plan, which is something you want to do that's a painful thing to do. If you change it a little bit, you can do it. You can just call the people who are involved in those changes. If you change it completely, you have to call everybody, gets everybody's approval. And I can assure you one person will not be okay with moving its shift because they have a birthday party somewhere that they need to attend, right? And they don't want to do a shift at that time. So, and of course, operational planning like technician routing and so forth. Any vehicle can break down. Any technician can call in sick for a day, and it can happen up to a few seconds before the execution starts, or even during when it happens, right? So in conference scheduling, we're assigning, just to explain a little bit how to think about this, we're assigning conference talks to rooms and time slots. So we have a number of rooms here, we have a number of time slots, we're assigning a number of talks to certain time centers. So we did this for DevOps last year with OptaPlanner. So the thing here is that when you look at the schedule, there's a call for proposals, there's a CFP deadline, there's acceptance of and rejections of proposals, at which time the solver can start deciding, after they know which talks will come there, which talk will be in which room and at which time, right? And so this is where we run the solver. After the proposals are rejected, unfortunately, we do not help in there. I would love to, so when they know these are the proposals we accept, then they decide which ones to publish. Now, then the schedule needs to be published. Now, the moment you publish a schedule, the speakers adjust their arrival times to jet, their flights or their trains or whatever the case may be, right? Their agendas, they block that out in their agenda. So afterwards, you really cannot change it anymore, the time of a time slot, or you need their approval when you do so. So you get a whole bunch of speaker and availability requests before you need to publish, so you take those into account, so you make sure you have a schedule that adheres to those. And then you get a whole bunch after you publish. Usually when you publish, there are some people say, okay, but I really can't because I already have an appointment and I forgot to tell you as an organizer. So you need to take those into account, and these come up later after you published. But again, the moment you've published, people adjust their schedule accordingly. And then, of course, you have the other things that might affect the schedule, especially the room, like favorite voting. So you want to rerun the solver with minimum disruption. So how do we do that there? Well, what we do is on the talk, so a talk is assigned to a specific time slot, right? But we also keep track of the published time slot, which starts out as NULL. So basically, once we say we're going to schedule, so we solve a problem with OptaPlanner solver, right? All the talks get assigned to its time slot. Then we publish it by basically copying this value into the published time slot value. And then when we get new input data, like for example, this speaker isn't available during that period, and now we need to rerun the solver, what we say is, okay, we're going to rerun the solver. So some of the talks will get assigned to new time slots, but we're going to add a constraint, as you can see here written in constraint streams, that we want to minimize the number of talks that gets assigned a new time slot that differs from the published time slot. So what we're saying is we're going to take a talk. If that talk's published time slot is if it's actually published, that talk. So if the speaker was informed, this is when your talk will be. And then we're going to check if the new proposal of that time slot, which hopefully solves our hard constraint that now one of the other speakers is not available, so we switch that with this talk with another speaker's talk. We're going to check if that time slot is the same as the published time slot. And if they're not the same, then we have a problem. We don't want to do that. We want to minimize it as much as possible. In fact, we only want to do that, and then we want to do that with a medium constraint. Why a medium constraint? We only want to change a speaker's time slot if it helps us to solve a hard constraint, because there's a new hard constraint in town that speaker Anne is unavailable on Monday, so we're going to switch her talk with Beth's talk, and so we're only going to switch that if it actually reduces the number of hard constraints, and we won't care about the soft constraints, right? So basically, if it reduces some of the soft constraints, we're not going to do it because then it's not worth it, because we have to call Beth, right? We have to call Beth and get her approval, and she might not approve. And if we have get approval from 10 speakers to get back to a feasible schedule, they all need to agree. If one of them disagrees, we're back at square one potentially. So that's normal. That's non-disruptive replanning with a medium penalty. So we disrupt only to become feasible again, right? Because there's new input data makes the original schedule unfeasible, even though it was feasible when we delivered it, when we published it. And there's also a soft penalty, disrupt if the gain is higher than a threshold. So in that case, we're saying, okay, you can actually disrupt the schedule as long as the gain is higher than if it's worth it, right? So for example, the room in conference scheduling, that's also published, but that can change far more easily because that doesn't affect people's arrival times and so forth. It's just their rooms, right? So we're much more freely there. So that's a soft penalty we're using there. I'm going to skip this, but this is basically the same idea on cloud balancing, where we say, yes, there's an optional, there's an original solution, but the problem that changed this computer broke down, where we have the disruptive solution, which is the highest possible solution, the best possible solution, the optimal one here. But we're not going to take that because it disrupts too much, too many things have to change. We're just going to go for a non-disruptive solution where we have far less movements, right? And this one is done with soft constraint, actually, right? Okay, so the next question is, and I'm running out of time, so
Don't worry. Yeah, go through it. It's exciting. Please go on.
Thank you, Karina.
Like something like 5 or 7 minutes later, so please go on.
Thank you, Karina. So it's the first time I'm doing this talk, and I'm running a little bit on my time.
That's why it's exciting. It's fresh new.
Thank you, Karina. So, does your problem change every few milliseconds, or every few seconds? Then we need to talk about real-time planning. Why? Because when you running the solver takes some time too. It could take maybe 5 seconds or 30 seconds or 5 hours, right? Usually somewhere between 30 seconds and maybe an hour, but that people run it. But that actually, you lose that time, right? So sometimes you want to have very quick responses. I can show a quick demo on that, but basically here we have the cloud balancing problem. We have a number of computers being assigned to processes, and what we can actually do in real time, click here to delete the computer, and OptaPlanner will these processes which are assigned to this computer will go unassigned, and OptaPlanner will then in real-time planning accept that change and immediately start assigning them again, right? And the whole entire thing takes 12 milliseconds. So don't blink when I push the button, right? So see, you didn't even see them appear at the top, or at least I didn't. And that's just because of how fast it is. I can show you in the logs. If you watch the logs here, and you go to the run here, over here, we look for restart. Okay, I've let it run too long already. But if you can actually see that the restart happens. Let me just do it again. Okay, it needs to solve, of course. We're solving. We kill this computer over here, right? And then we look for restart. I'll just kill it. You can see the solver restarted. And if you actually look at the timings here, this is the scheduling of the event. at second 11, and this is the restarted one at 11 seconds. And this is the end of the construction heuristic at 11 seconds, and at which time we're already feasible again, right? So all of the things are already assigned again. So that's really, and you can look at the milliseconds on how long it takes, but it's really not much time. Okay, so here we go. So real-time planning, basically we have a nightly plan, and then as the time goes by, we get new visits that get added in real-time planning, for example, vehicle routing, and we adjust our plans accordingly to pick those up. And as we actually do certain tasks, those tasks get pinned. Again, the use of planning pin is actually quite often here, right? And then of course, when you hear the yellow vehicle visit this customer, you can see all of these things get pinned, all the dark ones get pinned. And then, of course, as new customers come in, we adjust our plans accordingly. So that all uses the solver add problem fact change. The thing to know there is we have something called a daemon mode, which you can turn on. And why is a daemon mode? Basically, you don't want to waste CPU resources at the middle of the night, because when you have a solver running, and it's been optimizing for a while, and there's no real-time problem facts coming in, so there's no new customers that need to visit. The problem isn't changing, and it's always still solving. It's still taking CPU time. And what you can actually do is you can say, okay, I'm going to add a termination that says if there's no new input for a while, and your score has stabilized, and you don't find any improvements anymore, just block instead of actually using CPU resources. So the solver doesn't stop, it blocks in the daemon mode. And then as soon as a new problem fact comes in, it fires up again. So here we can see that. We provision, this is a case where we actually want to start a separate pod. But basically we say, okay, we add the vehicles, and then we add visits, and every time, this is a problem fact change, every time we add a new visit, it's actually, if you look at the log, the OptaPlanner is restarting in like 10, 12 milliseconds, right? And then new solutions come out, right? And the client accepts those. But if no new problem fact changes come in, and so no improvements for 20 minutes, it's actually going to go into this blocked state. This is the daemon mode. And it's going to just sit there because it says, okay, I can't really find better solutions anymore, no new best solution. I'm not going to continue wasting CPU resources. It's good enough. And then when a new problem fact comes in, it's a restart, and it starts solving again until again it hits that no improvement for 20 minutes, right? And of course you can configure all this, but this is interesting to keep in mind. Daemon mode can really be very good for the environment, because this is don't waste CPU resources and heat and electricity if you don't need to anymore, right? And then the last bit I want to jump into is the over constraint planning. And so what is this? Is that you have a resource shortage, right? You have too few nurses, too few employees in this case, we have too few CPUs, too few machines to actually do all of these processes. And you can see if we all schedule them, we always have at least 2 CPU too little. So what you basically do is, you want to have one of the resources unassigned to a null, right? That's one way of doing it. And the problem is, if you just assign all entities by default, you will break the hard constraint, but this is not a solution, because by default, OptaPlanner will assign every entity to a planning variable, never to null. Unless, of course, you say nullable is true. If you say planning variable nullable is true, then it will assign it there. And then you need to add a medium constraint, which checks, okay, how many of these are unassigned? And again, you penalize that, right? And you're probably wondering, what if I have over constraint planning, and if I have non-disruptive planning where I also have a medium constraint, how do I do that? You could actually use a bendable score to have 4 levels. So you can have hard, medium, next medium level, and then soft, or you could just sum them up in the medium level as you see fit, right? But anyway, combine these as you see fit. That is not a problem. So, like I said earlier, planning variable nullable is true. There's another way, that's virtual values of virtual resources. Christopher talked about that 2 days ago. Do take a look at his session on that. But basically, you add extra employees, which are virtual, and then you add in constraints that penalize the use of these, because basically these are interim employees, right? Or freelance employees that you hire on the spot, right? Consultants. And these are, of course, far more expensive than your normal employees. but sometimes you just need them to have a feasible solution to your problem. You cannot say in the hospital, freelance nurses are a well-known fact in hospitals. We cannot say we're not going to deliver our service to the patients, right? And the last one, we'll just skip quickly, is if you fear a worst case scenario, you want to look into backup planning. So what is backup planning? Is the way of adding constraints into your problem such that when something bad happens, there is no worst case scenario. At least the worst case scenario isn't that bad. So for an example in hospital bed planning is that instead of just allowing, it's trying to keep one bed open. Why is this a good thing? Then when a new admission comes in, a new patient comes in for a certain amount of period, it's likely you're going to have a continuous bed open for an amount of time, right? Other examples of this are having reserve employees, having employees assigned to a reserve shift, which actually spans the entire day, not a particular 8 hours, such that when somebody calls in sick, you can actually just use that nurse. That's called backup planning. And this could be a presentation on its own, so I'm just going to continue here, right? So don't make your plan a house of cards where you remove one card and the whole plan falls in. Even though it might look perfect as a house of cards, you may add on some robustness by adding constraints in the plans to make sure, which are domain specific, to make sure that when something bad happens, that it works out. So this is my presentation. So just want to remind you, know your toolbox, in this case OptaPlanner. Know there's multi-stage planning, continuous planning, non-disruptive replanning, real-time planning, over-constraint planning, and backup planning. And I hope by seeing this presentation, you get a good grip on what all of these things are. And you can combine them as needed. Yes, you can do continuous planning with real-time planning and non-disruptive planning and all these things together, but they are not Pokemon. You do not need to catch them all. Keep it as simple as possible. Only use the ones that your business requirements require you to use, of course. Thank you for watching.